Here's our next example using Stokes' theorem. For this example, again, we start with a vector field. Here our vector field f is given as follows: components x, y, z, x, y, and x squared y, z. And we'll start off here not giving a curve, but giving a surface. Our surface here is the surface S, which is described as follows. It's the top four sides, not including the bottom, of a cube with vertices at plus minus 1, and plus minus 1. So there are actually 8 vertices here, and they describe a cube. The cube is a cube with where each side has length exactly 1. I'll try to draw a picture of the cube. So let me plot the vertices. Of course, where's plus 1, right here in the xy plane. X plus 1, y minus 1 right here. X minus 1, y minus 1 right here, and y minus 1, or y plus 1, x minus 1 back here. And then, of course, we have the z coordinates plus minus 1 as well. So that's here, 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 and here. So we have those 8 vertices. And now we can connect those with lines. As follows, to build the cube. Okay, so there's our cube. It's close enough. What are the sides of my cube? Well, you can see the sides. For example, here's one side right here. There's the front side, and the back side, and the top. So the surface S, forgive this terribly cluttered picture now, is the top and all 4 sides of the cube, not including the bottom. So the problem here in this example is the following. Use Stokes' theorem to find the flux of the curl of f through this surface S. So we'll use Stokes' theorem by calculating instead the line integral of the vector field around the boundary of S. So what's the boundary of S? Well, the boundary of X is basically just the bottom edge of the box, since we did not include the bottom surface of the box. So here I've indicated this with the curve C oriented in a counterclockwise fashion as follows. Now, remember that this is actually at the z coordinate, z equals -1. So this is a square that we're traveling around in a counterclockwise direction, and this square is restricted to the z equals -1 plane. That's where the bottom of the box is. So here's Stokes' theorem. The flux of the curl can be rewritten as the line integral of f around this curve C. So now let's calculate this line integral. Here what I've done, I've taken the curve C, which, remember, I'll draw it again. The curve C actually lies here, floating in XYZ space, but I've taken it and looked at it from the top down to obtain this representation of the curve C. But I have to remember that the z coordinate is -1 everywhere. So here it is. I'm breaking the curve up C into 4 piecewise smooth pieces, C1, C2, C3, and C4. And then the line integral C over C can be written as the sum of these 4 line integrals. So I break it up into 4 little separate problems. So the bad news is that we have to calculate 4 different parameterizations of these 4 different C1, C2, C3, and C4s. So here's C1. I'll remind you of this picture. C1 goes like this, and the z coordinate is -1, and I've indicated that here. But the x and y coordinates do what? Well, the x coordinate is fixed at 1. The y coordinate goes from -1 up to 1. So that's why we see the y coordinate varying as t, where t goes from -1 to 1. So that's the path C1. And we take the derivative, r prime of t of this thing, which is just 0, 1, 0, because remember, we need this for the parameterization. Let's look at it. Here's the line integral f along this first portion of the curve C1. Here's its parameterization from -1 to 1. And so now we fill in these blanks. When we evaluate f at this particular parameterization, remember the vector field f is defined as x, y, z, x, y, z. I think it's, and then xy, and then x squared y, z. So we fill in those coordinates x, y, z, referring to this RT up here. And then we dot product this with r prime t, which was taken right here. And when we take the dot product, we just get, well, integral of t from -1 to 1, and that's just 0. So the line integral of f along the curve C1 is 0. Now we still have the line integral of f around the remaining curve portions, C2, C3, and C4 to worry about. I'm not going to spend the time to go through those step by step. I will briefly provide them here on the screen. You can and should do them yourself, but double check your work by pausing the video if you like. So here comes C2. Here's the parameterization for C2, and the line integral C2 using the parameterization we again find is 0. Next up will be C3. Here again we parameterize C3. Line integral over C3, that should reach C3 down there. Again we find 0. And next up C4. Parameterization of the fourth line segment C4. Line integral along C4. Again we obtain 0. So what's the conclusion at the end of the problem? Well, remember we were originally tasked with finding the flux of the curl of f across or through this surface S, which was the top and sides of the cube. We rewrote that via Stokes' theorem as the line integral of f around the boundary of S, which is the bottom edge of the cube going around the four sides. And we found that that was just 0 plus 0 plus 0 plus 0, or 0. So the flux of the curl of f through this cube is 0. No deep significance to the fact that we got 0. We did everything correctly. That's just the answer for this case. In particular, let me make this remark before we end. You may be tempted to guess that this entire flux is 0 because maybe perhaps this curl is 0. Maybe. But in fact, you can check that the curl is not 0. That's a direct calculation. You get a non-zero vector for the curl. So having a curl of 0 would certainly be sufficient to give you 0 here, but it's not necessary. You can also get a flux of 0 even if this curl is non-zero, which is the case here.